Hi everyone, today we are discussing about the electrostatics, and in this topic we are discussing about the properties of the charges. In these charges, the charges are exist only two types of charges, namely positive and negative. Like charges repel, unlike charges attract each other. Charges is a scalar quantity. Charge is predictable in nature. Example, positive 2 charge, positive 5 charge minus negative 3 charge is equal to positive 4 charge. Charge is quantized, that is, electric charge exists in discrete packets rather than in continuous amount. It can be expressed in integer multiples, fundamental electronic charges. Charge is conserved, that is, the algebraic sum of positive and negative charges in an isolated system remains constant. Example, when a glass rod is rubbed with silk, negative charge appears on the silk and an equal amount of positive charge appears on the glass rod. The net charge on the glass silk system remains zero before and after rubbing. It does not change with velocity also. Note, recently the existence of squares of charge 1 by 3 electrons and 2 by 3 electrons has been postulated. If the quarks are detected in any experiment with concentric particles evidence, then the minimum value of the quantum of charge will be either 1 by 3 or 2 by 3 electrons. However, the law of quantization will hold good. And Coulomb's law. The force between 2 points electric charges. The electrostatic force of attraction or repulsion between 2-point electric charges is directly proportional to the product of the charges, inversely proportional to the square of the distance between them, and the adds along the line joining the two charges. Strictly speaking, Coulomb's law applies to stationary point charges where the K is a positive constant of electrostatic force constant or the Coulomb's constants, where epsilon is the permittivity of the free space. In the medium, constant K is equal to 1 by 4 by epsilon, where epsilon is the absolute electric permittivity of the dielectric medium. The dielectric constant or relative permittivity or the specific inductive capacity or dielectric coefficient is given by K is equal to epsilon or is equal to epsilon by epsilon naught. In vacuum, force is equal to 1 by 4 by epsilon naught into Q1 Q2 by R square. In medium, force F is equal to 1 by 4 by epsilon naught epsilon R into Q1 Q2 by R square. The electric field. The electric field is a region of space around a charge or a system of charges within which other charged particles experience electrostatic forces. Theoretically, electric field extends up to infinite, but practically it is limited to a certain distance. Electric field strength at a point in an electric field is the electrostatic force per unit positive charge acting on a vanishingly small positive test charge placed at that point. The test charge is considered to be vanishingly small because its presence should not alter the configuration of the charges and thus the electric field which is intended to be measured. The electric lines of force due to a uniform field. The properties of the electric lines of force or electric lines. The electric lines of force are imaginary lines. A unit positive charge placed in the electric field tends to follow a path along the field line if it is free to do so. The electric lines of force emitted from a positive charge and terminate on a negative charge. The tangent to an electric field line at any point gives the direction of the electric field at that point. Two electric lines of force can never cross each other. If they do, then at the point of intersection there will be two tangents. It means there are two values of the electric field at that point, which is not possible. Further, electric field being a vector quantity, there can be only one resultant field at the given point, represented by one tangent at the given point for the given line of force. The electric lines of force are closer where the electric field is stronger, and the lines spread out where the electric field is weaker. Electric lines of force are perpendicular to the surface of the positively or negatively charged body. Electric lines of force constants lengthwise to represent attraction between two unlike charges. Electric lines of force exert lateral pressure or represent repulsion between two like charges. The number of lines per unit cross section area perpendicular to the field lines, that is density of lines of force, is directly proportional to the magnitude of the intensity of electric field in that region. So the formula is delta N by delta A directly proportional to E. Electric lines of force do not pass through a conductor. Hence, the interior of the conductor is free from the influence of the electric field. Electric lines of force can pass through an insulator. Electric dipole. The electric dipole is a pair of equal and opposite charges separated by a very small distance. The electric field produced by a dipole is known as dipole field. The electric dipole moment is a vector quantity used to measure the strength of an electric dipole. The magnitude of electric dipole moment is the product of the magnitude of either charge and the distance between the two charges. The direction is from negative to positive charge. The SI unit of the P is coulomb meter cm. Note: an ideal dipole is the dipole in which the charge becomes larger and the separation between smaller and smaller. Area vector. A small area of a surface can be represented by a vector ds bar equal to ds n cap. Electric flux. The electric flux linked with any surface is defined as the total number of electric lines of force that normally pass through the surface. Electric flux d phi through a small area element ds due to an electric field E at an angle theta with ds is d phi is equal to E into ds, that is E ds cos theta. The total electric flux phi over the whole surface S due to an electric field E is phi is equal to integral surface S E into ds, that is Es cos theta, and the result is E into S. The electric flux is a scalar quantity, but it is a property of vector field. SI unit of electric field is nms square C minus 1 or joule meter centimeter. Behavior of the conductors in the electrostatic field. Net electric field intensity in the interior of a conductor is 0. When a conductor is placed in an electrostatic field, the charges drift towards the positive plate, leaving the positive core behind. At an equilibrium, the electric field due to the polarization becomes equal to the applied field. So the net electrostatic field inside the conductor is zero. The electric field just outside the charged conductor is perpendicular to the surface of the conductor. Suppose the electric field is acting at any angle other than 90 degrees, then there will be a component E cos theta acting along the tangent at that point to the surface, which will tend to accelerate the charge on the surface, leading to surface current. But there is no surface current in electrostatics. So the theta is equal to 90 degrees and cos 90 degrees is equal to 1. Net charge in the interior of a conductor is zero. The charges are temporarily separated. The total charge of the system is zero. Flux is equal to integral surface E dot ds is equal to q by epsilon naught. Since the E is equal to 0 in the interior of the conductor, therefore q is equal to 0. Charge always resides on the surface of a conductor. Suppose a conductor is given some excessive charge q. Construct a Gaussian surface just inside the conductor. Since E is equal to 0 in the interior of the conductor, therefore q is equal to 0 inside the conductor. Electric potential is constant for the entire conductor. dV is equal to minus E dot dr. Since the E is equal to 0 in the interior of the conductor, therefore dV is equal to 0. That is, vector is equal to constant. Principle of capacitance. Plate A is positively charged and B is neutral. Step 2. When a neutral plate B is brought near A, charges are induced on B such that the side near A is negative and the other side is positive. The potential of the system of A and B in step 1 and 2 remains the same because the potential due to positive and negative charges on B cancel out. Step 3. When the further side of B is earthed and the positive charges on B get neutralized and the B is left only with negative charges. Now the net potential of the system decreases due to the sum of positive potential on A and negative potential on B. To increase the potential to the same value as was in step 2, an additional amount of charges can be given to plate A. This means the capacity of storing charges on A increases. The system so formed is called a capacitor. Energy stored in a capacitor. The process of charging a capacitor is equivalent to transferring the charges from one plate to other of the capacitor. The moment charging starts, there is a potential difference between the plates. Therefore, to transfer charges against the potential difference, some work is to be done. This work is stored as electrostatic potential energy in the capacitor. If dq be the charge transfer against the potential difference V, then the work done is du is equal to W is equal to V dq, that is q by c dq. The total work done to transfer charge q is u is equal to integral 0 to q by c dq. And the Gauss law. Gauss law states that electric flux through any closed surface is equal to 1 by epsilon naught times the total charge enclosed by that surface I equal to 1 by epsilon naught u. Applications of Gauss law. It is used to find electric field intensity at some distance due to distance charge distribution. Over single isolated charge, we use E is equal to constant K Q by R square to find electric field intensity. But we can apply this formula for multiple charges. So we use Gauss law to find electric field intensity more than one charge.